how's everybody doing out there? Well, welcome to lucky day 13 of Corona Online School. So, hopefully, everybody did a good job finishing up the chapter 3 stuff and finishing up our unit, almost partway through our unit 2 material here. So, in this section, we're going to start talking about factors, divisors, multiples. So, like, eventually, we're going to talk about like least common multiples, greatest common factors. We're going to talk about prime numbers, divisibilities. There's all kinds of stuff going on in this section. So let's kind of start off right away and look at example 1 here real quick. So what multiplication sentence does the below array demonstrate? And so hopefully at this point you're yelling out that there's 2 different possible answers, because if we think about it this way, I can see I've got a row of 4, and how many rows of 4 do I have? I have 3 of them, so I've got 3 times 4, because I've got 3 rows of 4. Or, if I think about it the other way, let's erase these guys, I could think about them up and down as a column of 3. And how many columns of 3s do I have? I have 4 of those columns of 3. So I could write this as 4 times 3 in a column in that case. So just like we saw before, with multiplication, it's commutative, so you can, flip the order of multiplication and stuff like that. And so this array allows us to think about it a couple different ways as well. All right, so let's look at example 2 and talk about some of these. So we've got a little word bank above, and we want to try to fill them into the right spot down below. So our word bank is divides, factors, multiple, is divisible by, even, odd, divisors, and divided by. So 3 and 4 are blank of 12. So in this case, hopefully everybody's yelling out that 3 and 4 are factors of 12. Because if you think about 12, you can rewrite it as, 3 times 4, for example. So the fact that we can write it as 3 times 4 means that 3 and 4 are both factors of 12. All right, so 3 and 4 are blank of 12. So there's another thing that we can do here. So 3 and 4 are also divisors of 12, because they can divide into 12 evenly. That takes care of divisors. So 4 blank 12. So in this case, 4 divides 12. Let's see. So 12 blank 3. So 12 is divisible by 3, is what we're looking for here. And so 12 is a blank of 4 and 3. So in this case, 12 is a multiple of 4 and 3. So multiple just means, like, if you went through and started with 3, and then doubled it, would get 6. And then, times it by 3, we'd get 9. So it just kind of goes through all the different possibilities of 3. So 3 is a blank number. So this would be odd number. Oh, I forgot to scratch off multiple. So we're down to 2 left here. So 4 and 12 are even numbers. And then finally, by process of elimination, 12 divided by 3 equals 4. So it looks like we got them all right. So hopefully everybody got those same answers at home when you were working on it on your own there, hopefully. So these are kind of the terminology that we're going to be using in this section. So just kind of keep in mind what each one means. So if they ask you a question about it, whether we're looking at factors or multiples or divisors, any of those things. So, all right, so let's take a look at example 3, 4, and 5 here real quick. So 4 says list the first 10 positive multiples of 4. So again, with this, what we do is we just start with 4, and then we just kind of multiply that number by the first 10 numbers. So 4 is basically 4 times 1. So then 4 times 2 would be 8. 4 times 3 would be 12. 4 times 4 is 16. 4 times 5 is 20. 4 times 6 is 24. 4 times 7 is 28. 4 times 9 is 36. And then finally 4 times 10 gives us 40. So that's our first 10 multiples of 4. And we can keep going forever. You know, like multiples go on and on and on and on forever. There's no stopping because you can just keep, adding 4 to the next one and just keep going on and on and on forever. All right, so let's do the same thing for 3. So for 3, we've got to start with 3. So again, that would be 3 times 1. 3 times 2 is 6. 3 times 3 is 9. 3 times 4 is 12. 3 times 5 is 15. 3 times 6 is 18. 3 times 7 is 21. 3 times 8 is 24. And then 3 times 9 is 27. Oh, I'm losing track here. 3 times 10 is 30. Sorry. All right. And so one of the things that we're going to look for eventually is what's called the least common multiple of a number. And so we won't officially go into this until the third section in this chapter. But one of the techniques that we can use is actually doing this kind of stuff here by actually listing out the multiples and then trying to find the smallest one that both of them have in common. So if we kind of look on our list, are there things that appear in both of these lists? So I can see that there's a 12 in this list, there's a 12 in this list, there's a 24, there's a 24. And if we kept going, there'd be more and more and more of these multiples that they had in common. But if what we're looking for is the least common multiple, then that means we're looking for the smallest number that both of these guys actually have in common. So in this case, we'd be looking for the one that's the farthest on the left. So in this case, 12 would be the least common multiple of 3 and 4. So again, kind of keep that in mind. We'll do it more later on, but it's a nice opportunity to kind of look at it with it being laid out in that multiples term. All right. Is everybody okay with being able to list out multiples? All right, very good. So now what we want to do is list all the divisors. So these are the things that divide into 12 evenly. So the thing to remember about this, and you don't have to write them this way, I like to think about them this way because it helps me not forget any, is whenever we're doing divisors, we're always going to have like matched pairs that go together. So for example, 1 divides everything, so 1 should always be on your list when you're talking about divisors, and so, or factors. But the thing that pairs up with 1 in this case would be 12, because 12 divided by 1 gives us 12, or 1 times 12 gives us 12. So we're always thinking about that kind of multiplication. So in this case, since 12 is even, we know 2 goes into it, and the thing that goes with it would be the 6 in this case, because 2 times 6 gives us 12. And then finally, 3 goes into it, and 3 times 4 gives us 12, so 4 would be our other one. So in this case, our only factors now left a big gap in the middle because I didn't know how much room we were going to need. So let me tighten this up a little bit here. So our only divisors or factors are going to be 1, 2, 3, 4, 6, and 12. So again, remember, we always get 1 and we always get the original number back again. So those are always going to be part of our divisors in this case. All right. Is that okay with everybody? So if you get stuck on any of these while you're working, definitely let me know. So, all right, so let's move on to the next example here. So this one, even though I wrote it as an example, this one's going to actually be for you to work on your own. And you can check with me if you have any questions. But basically what we're going to do is, this is what's called the sieve of Eratosthenes. So this is kind of a the technique that was developed a long time ago to figure out what numbers in a list of numbers are primes. So what you're going to do is just follow, step A through G here to figure out all the prime numbers between 1 and 100. So first off, you might be wondering, what is a prime number? So in case you've forgotten, so numbers are basically broken into prime or composite, except for 1 and 0 in this case. But so a prime number means that the only number that can divide it is 1 in itself. So basically, what we did up here with number 5, when we listed all the factors, a prime number is just going to have the 1 and then the number itself. There won't be any numbers in between. So there's only going to be 2 factors in that case, 1 and the whole number itself. So 3, for example, is a prime number, because if you were to break it up into its factors, it's just going to be 1 and 3 in that case. And so basically a number is either prime, which again means it can only be divided by itself in 1, or it's composite, which means it's made up of a product of prime numbers. And it can have lots of different factors and stuff. So in this case, so again, 1's not considered prime or composite, so we just kind of throw it out the window. And then what it says next to do is circle 2 and then cross out any even numbers. And then just kind of keep following that technique. And then when you're done, unpause the video and then come back, and then we'll move on from there. So what I'll do is I'll have you guys maybe post up your prime numbers to make sure we got all the same prime numbers, make sure we didn't miss any or anything like that. And we'll check each other's work on the collaboration. So, all right, so when you're done, come on back and we'll move on to the next example. All right, so here again, I kind of summarize what the definitions of prime and composite number are for you. So again, a prime number is a natural number that has exactly 2 different factors, 1 in itself. Composite, I can't spell composite apparently. Number is a natural number that has more than 2 different factors. And so all composite numbers can be written as a product of prime numbers. And so that's going to be important because we're going to use that a lot later on. All right, so for example 7, what we're going to do is we want to write the number 100 in what's called prime power representation form and then list all the divisors of 100. So I'll talk a little bit more about what prime power representation form is when we get there. But for right now, what I want to do is factor 100 by using what's called a factor tree. So if you haven't seen one of these before, if you've forgotten, I'm going to show you how to do it. So basically what you do is start and put 100 at the top, and then what we're going to do is make a bunch of branches off of 100. And so you can do this lots of different ways. Like you may notice that 100 is 10 times 10 and kind of start there. For me, I typically like to start with like prime numbers and kind of work my way through prime numbers. I mean, there's no right or wrong way to do this as long as you end up with the same factorization at the end. The main thing is what we want to do is we want all of our branches to stop at prime numbers. Like we wouldn't want to stop with 10 and 10 and be like, okay, boom, there's my factor tree. So we have to keep going so that everything that's the only numbers that are left that are being multiplied together are going to be these prime numbers that we found above. So for that reason, a lot of times what I'll do is I'll start with like, since it's an even number, I know 2 will divide into 100. And so I'll just do 2 times 50 to make my first branch. And then what I do is I kind of circle every time I get to a prime number, because that means, okay, I'm done. I can't go any more down that branch. That branch is stopped. And so then I would do 50. So again, 50 is even. So I would divide 2 into 50. And so that's going to give me 25. And so again, notice I circled the 2 because 2's prime. And then 25, so it's not even anymore. So you might as well stop using 2. 3 doesn't go into 25, but it turns out 5 does. And so we end up with 5 times 5, and hopefully you saw from above that 5 is also a prime number. So I'm going to circle both of those, and so our branch is officially over. And so to multiply these guys together, what we're going to do is just multiply all those things that are circled together to get our product of primes. So right, 100 is a product of primes, and it's going to be 2 times 2 times 5 times 5. All right. So that's how, again, so 100 is a nice composite number that we just showed because it can be written as a product of primes. So prime power representation means to write these with an exponent form. So we want them to be in their prime form, but instead of writing 2 out a bunch of times or 5 out a bunch of times, we want to simplify it and write it in terms of exponents. So in this case, since we've got 2 2's, this would be 2 squared times 5 squared in this case. So that would be our prime power representation of 100 in this case. All right, so now we're looking for how many divisors does 100 have. So this is the same thing we did above with 12. Like, I forget what example it was, example 5. We were looking for how many divisors. So with this one, we'll probably have to do E first, just because, you know, unless you have some magic formula or something like that to figure out divisors, it's kind of a brute force method where you really just have to list out every single one of them. And so this one's going to have a lot, so this is one of these nice opportunities to, you know, kind of jot down the pairs as you're going along. Now the good thing is, since we know the only prime numbers that are going to go into it are 2 and 5, then that means there are certain things we don't have to check, like 3, for example. We don't have to check and see does 3 go into 100, because if it did, it would be in the prime power factorization. So what we're going to do is we're going to use kind of different combinations of these 2's and 5's together to come up with all the different possible factors of 100. So again, the way you should always start is it should be, you know, the extremes first. There's always 1 and 100 in this case. And so since there's 2 goes into it, I know 2 will go in, and that'll give me 50. So now I'm actually going to use, and I'm going to try to keep them in order just to make it a little bit easier to keep track of. So I don't want to jump straight to 5 because 2 squared is 4 and it's smaller than 5. So that means 4 goes into 100, which would give us, what is it, 25 it looks like. All right. Now I'm going to jump to 5 in this case. And so 5 goes into 120 times. And then again, I don't have to check 6 because there's no 3. I don't have to check 7 because there's no 7. I don't have to check 8 because there's no 2 to the third. So I don't have to worry about 8. There's no 9 because there's no 3. So I do have to check 10 because I can multiply 2 times 5. And that would give me 10 in this case. And so that gives me, oops, well, that's the same number. So it looks like we've met in the middle. So I don't need to write that twice. So that should give us everything then. So, because that's what will happen when you do this. You'll either duplicate something or you'll end up kind of meeting in the middle. So it looks like our possible divisors are going to be 1, 2, 4, 5, 10, 20, 25, 50, and 100. So this was one, oops, I'm just erasing stuff here. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So it looks like I've got 9 divisors total. And so in this case, it also asked us to write them in exponential form. So I do have you practice this a little bit. I'm not too worried about this because it's a little bit messy at times, but the nice thing is if you get used to doing the exponential form, it kind of guarantees that we didn't miss any on our list, which is the idea. So what we're doing with exponential form is kind of going through every single possibility of the 2's and 5's with the exponents together. So the key to this is trying to keep everything as kind of organized as possible. So what I mean by that is what I'm going to do is I'm going to write these in column forms, and I'm going to fix one number to always be the same, and I'm going to cycle through all the possibilities of the other one. So in the first column, basically I'm going to fix 5 to stay 5 to the 0. And then I'm going to cycle through 2 to the 0, 2 to the 1, and 2 squared. So in this case, I'm going to get 2 to the 0 times 5 to the 0. And so I'll just kind of tack along what number this is equal to as we go along so we can make sure that we knock every one of them off our list. And so now I'm going to leave 5 to the 0. Then I'm going to bump up to 2 to the 1 times 5 to the 0. So that gives me my 2. So I got the first 2 on my list. And then again, leaving 5 to the 0, now I'm going to go up to 2 squared. And that gives me my 4 in this case. So now, my second column, I'm going to fix 5 to the 1, and then again cycle through all the 2's again. So in this case, I'm going to get 2 to the 0 times 5 to the 1, which is just going to give us the 5. And then 2 to the 1 times 5 to the 1 gives us the 10. And then 2 to the second times 5 to the 1. So 4 times 5 gives us 20. So it's looking pretty good so far. We haven't, encountered any new ones that aren't on our list. So it looks like we probably did a good job. So now finally, the last step, I'm going to fix 5 to be 5 to the second and cycle through all the 2's. So in this case, 2 to the 0 times 5 squared is 25. Oops, that was ugly. 2 to the 1 times 5 squared is 25 times 2 is 50. So we got that. And then finally 2 squared times 5 squared gives us the 100. So that's what they mean when they say write the divisors in exponential form. So again, you could have done it that way. So instead of trying to shoot the list out like I did, you could have just actually wrote these all in exponential form first. And if you do it in this nice order like I did, it kind of guarantees that you don't miss anything along the way either. So keep that in mind. However you like to do it, it's kind of up to you. All right, so at this point, pause the video, work on practice 1. So this is going to do the exact same thing we did above, except for we did it for 100, and you're going to do it for 90. So pause the video, work on practice 1, and then when you are done with that, unpause the video, and we'll come back and we'll talk about infinitely many primes. All right, so the big thing is, you may or may not know this, so it turns out that there are actually infinitely many primes. So primes go on and on and on and on forever. And there's actually a lot of people out there that are actually trying to find, there's always people trying to find the biggest prime number. And, the bigger the prime number, the better. And they're actually kind of hard to find. So people are actually patenting big, large prime numbers because they can be used for, encoding information. So a lot of people are using them as a cryptography type thing. So for example, whenever you make a purchase on Amazon, how do you know your credit card isn't going to get stolen? Well, there's this high level of 256-bit encryption. And so this encryption is actually using large prime numbers to actually embed these the data. And so it's really, really hard to break these codes because it's really, really hard to determine if a number is prime or not. And so it's a lot more complicated than that, and I don't want to get into the details of it. But the fact that, people are actually trying to find prime numbers just so they can patent them to make money off of them is kind of a weird thing, but it is what is going on. And so for us, we're going to try to figure out, even for small numbers, it's sometimes hard to figure out whether a number is prime or not, short of just brute force. And that's what we're really going to do. But what I'm going to do is show you a little technique that'll help at least eliminate some of the possibilities. Because if you saw on that first page we had, there was probably 20 or 30 some primes, a bunch of primes on there. And so, do you want to divide, try every 20 or 30, or you only have to try a couple? So the key is, if we look above, is that if we start by trying to find the square root of the given number, and then jot that down somewhere, and then once we get that square root, what we want to do is list all the prime numbers that are less than that square root, test those guys, see if they divide into it, and if any of them divide into it evenly, then it means the number is not prime. If none of those work, then it means the number is prime. in this case. So for us, what we're looking at is we want to try to figure out whether 101 is prime or composite. So the first thing we should do is find the square root of 101. And this is going to be bad because I forgot my calculator. So let me flip to the calculator thing here real quick. So I know the square root of 101 is 10 something. Nope, that's not what I want. Let's put it in decimal form. Oh, square root of 1. Oh, jeez. Getting worse and worse here. There we go. 10.049. So in this case, we're only worried about the whole number part of it. So in this case, I'm going to jot down. So it's approximately 10.04 in this case. And so what I want to do is I want to list all the prime numbers, less than that 10.04. So if we remember on our chart, there should be 2, there should be 3, there should be 5, there should be 7, and that should be it. Those should be the only ones. And so now what we want to do is kind of divide each one of these numbers in and see if any of them divide in evenly. So we're going to learn some tricks next time that's going to allow us to look at some of these things real quick and kind of eliminate. Like, for example, is 2 going to divide into 101? No, I don't even have to test that because 101 is not an even number. So I don't even really need to test 2 because it's not even. And what about 5? Is 5 going to divide into it? Well, hopefully somewhere along the lines you've learned that, a number is only divisible by 5 if it ends in a 0 or a 5. If you forget, you can, there's not that many to test. You can throw these into the calculator. But in this case, 5 is not going to work either because it doesn't end in a 5 or a 0. And so there's rules for 3 and 7, but I'll go ahead and test these just to see real quick. So let's do 101 divided by 3. And so since we get a fraction, that's no good. Or a decimal, that's no good. And then 101 divided by 7. So again, same thing, we got a decimal. So again, in this case, that's all we have to test is just those couple numbers. So now we know for certain that none of the numbers under 10, none of the prime numbers under 10 go into it. So this means that 101 is prime. All right. Is that okay with everybody? All right, perfect. So I'm going to have you guys go through practice 2. So again, it's doing the exact same thing. It's actually just, divide 1001 by, or take the square root of 1001. List all the prime numbers using that sheet that you made in example 1. Test them, divide them in, see if any of them work. If you find one that works, of course you're done at that point. It's composite. You don't have to test the rest of them. But if you're unlucky and you have to go through all of them and none of them work, then that just means it's a prime number. So work on practice 2. So work on practice 3. So this one's actually getting us into greatest common divisor, kind of doing a little bit of the same trick that I did above. So if you get questions on 3, so again, this is just kind of preview of what we're going to do in the next in the 2 sections from now. So if you get stuck, just let me know. And then 7, again, just another practice if it's prime or not. So again, if you have questions about it, just let me know. But otherwise, I'll be around the computer all day tomorrow. So good luck and have fun playing with all these different factors and prime numbers.